So good morning and welcome to Tucson. We're really excited to have you here. It's, as you will see, it's a great place, and I hope that you will like the program we put together. There is a lot of free time, and this free time is not just to party. It's also to interact with each other and also, very importantly, interact with the faculty. And Peter, it's also for you, not just a party. So I have a couple of things that I really need to tell you because they are important. First of all, you may already have noticed that this is a very isolated place. What it also means is that it's in the middle of the desert, and it comes with all kinds of interesting features. One of the features is that there are kinds of wild animals around here. This is the winter, so you will not see rattlesnakes, I think. But when you walk around at night, you might see coyote, you might see bobcats, maybe even a mountain lion, javelinas. So always take a flashlight with you. It's also very dark at night, okay? So just be a little bit careful because, I mean, there are very few mountain lions around here, but they are above you in the food chain. Okay? So just be a little bit careful and always take your flashlight. This is the most important thing. There is wireless everywhere. You don't need a password for wireless, so just go ahead and use it. If you have a phone, and especially if you have AT&T, you will have noticed that reception is really shaky. You will see a lot of people walking around looking for a bar. But Skype works great, of course. So, and I think Verizon works a lot better than AT&T. So this is a bit of a problem. A couple of things. So you've all met Naomi. Naomi has done all the real hard work here, and thank you so much. She's also organizing outings. We will have an outing on Monday, and you have a choice between a hike in the Catalina Mountains, which are very beautiful, but you need sturdy shoes, and you need to take a lot of water. It's very dry around here. Or you may choose to go to the Desert Museum, which is a world-class, spectacular mixture of a zoo and a museum, which explains everything about the life and the plants and the nature in the Sonora Desert. So both choices are available, but it's important that we have you sign up today so that we can reserve the buses of appropriate size. Okay? So please do it by the break. Okay? So that's one thing. Another thing is that on Saturday night, the Astronomy Club of Tucson will come with a bunch of telescopes, and we'll have a stargazing party. And this should also be very spectacular because it's very close to the new moon, and the sky here is really great. So that should be a lot of fun to have that. And also, you may have seen this very weird structure called the Biosphere 2. We have a tour organized for you. I don't know which day. Is Kim here? Do you know? Naomi, you know when the tour of the Biosphere will be? I think it's Tuesday next week, but I'm not sure. Don't quote me on that. We'll figure it out for you. And I know that several of the faculty members won't be there at the time, so we will certainly arrange for everybody to have a chance to see this very unusual place, okay? So that's really, I think, pretty much all I have to tell you right now. I hope you have a lot of fun. You will see your casitas all have this common room so you guys can mingle and discuss and have a great time. And hopefully we'll all learn a deal of really good physics here. So now we can start with the program. You will see in the program that the first lectures are actually with two speakers, Steinke and me. I've had a couple of health issues lately, which didn't kill me, but kind of slowed me down a bit. So we prepared these lectures together with Steve. Steve is a research associate who spends half his time in Tucson and half his time at Caltech. He is a much better lecturer than me anyway, so he will give these lectures. And the only goal of these lectures is to make sure that we all have some kind of a common basis, that we remember what the Rabi frequency is, that we remember what the master equation is, the Bloch equations, and things like that, so that the people who will give the real lectures don't have to repeat all these things for you. So without further ado, Steve.
Well, as Pierre mentioned, this is just going to be an overview, actually, of basically all the, is it just me or is that a little bit annoying? Buzz. Oh. All right, I think I'm going to stick the mic then. Okay. It's feedback. Okay. There's two types of physics in the universe, as Pierre likes to mention, and basically in the first lecture here today, we're going to go over both of those, the two-state system and the quantum harmonic oscillator. And then we'll go through a few very simple examples just to make sure everybody is up to speed and refreshed on that. And then in the second lecture, we'll basically be talking about open quantum systems. So, the simplest non-trivial example of a quantum system you can come up with is a two-level system with just an excited state and a ground state separated by some frequency, omega. Now, we can write down the wave function in terms of a time-dependent population in the ground state, a frequency, a phase rotation due just to the ground state energy, and then a spatially dependent wave function. And then we can write down a similar piece for the excited state. So instead, what we usually do is write down kind of a vector representation of spin with the ground state represented by one basis vector and the excited state represented by the other. Very basic stuff. And of course, we can write down all the Hermitian traceless operators, a basis for the Hermitian traceless operators that might act on this two-dimensional system. And of course, we can also include the identity, which will commute with all of these. And then the commutation relations for the Poly matrices, remember, are sigma x. Okay. Commutation relations between these are non-trivial. You have, for example, sigma x and sigma y commute, they give you 2i sigma z. And so forth. And for cyclic permutations, you get similar relationships. We can also write down spin ladder operators, operators that raise and lower the spin by taking linear combinations of sigma x and sigma y. Now, these are not Hermitian operators. As you see, if I take the Hermitian conjugate of sigma plus, I get sigma minus and vice versa. So the reason why we call these ladder or raising and lowering operators is because if I act on the excited state with sigma minus, it gives me the ground state. So it lowers the system from its excited state to the ground state, and vice versa. If I act with the raising operator on the ground state, I get back the excited state. And so the commutation relation for sigma plus and sigma minus, and then if I commute, then I get sigma. And so the kind of simple, generic two-level Hamiltonian that we typically write down, the archetypical example, is just proportional to sigma z, and we can always change our basis by unitary transformation to write down this kind of Hamiltonian. And the atomic frequency here is omega A, that's this transition frequency. Now, let's switch to the only other important physical system in the universe, the simple harmonic oscillator. And in the classical, this has a classical analog, and that's just the typical mass on the end of a spring system, where the Hamiltonian has a kinetic piece and then a potential piece, which is just quadratic in the displacement. Now, in quantum mechanics, to satisfy the canonical commutation relations, we can, in the position representation, write down the momentum operator as proportional to the derivative of position. And so we can write down this Hamiltonian in a position space representation as a second derivative plus a potential term. And this is fine for, say, solving to find the ground state wave function and such, but an elegant approach is to use creation and annihilation operators So we instead take kind of this algebraic approach. We write down dimensionless operators A and A dagger, which are again linear combinations of position and momentum. And if I go back, you notice that they're kind of similar in form to the raising and lowering operators that I wrote down here, where it's a sigma x plus I sigma y. And here we're writing down Q, the position, plus I times the momentum, essentially rescales the same units. Now, I can invert these relationships and get the position and momentum operators written in terms of the operators A and A dagger. And the A and A dagger are dimensionless, and so I have to multiply by a quantity with dimension of position or momentum, and these are often called the 0-point position, the 0-point momentum, because in the ground state, that is the RMS value of the position in the momentum table. Now, the commutation relations for the raising and lowering operators, we plug in, you can just plug in the definition and work out that this commutator comes out to 1 if we know that Q comma P is IH bar, then what we get for A comma A dagger is 1. Now, making the substitution for these definitions back into the original Hamiltonian, we get the archetypical harmonic oscillator Hamiltonian, which is just H bar times the mechanical frequency times A dagger plus 1/2. Oftentimes in quantum optics, since this is just a constant, additive constant applied to the Hamiltonian, we can throw that out. And so typically we just see H bar A dagger A. That's the canonical harmonic oscillator Hamiltonian. Now, what are some properties of the raising and lowering operators? Well, the details are sparse here, but you can basically look at the eigenstates of the operator A dagger A. And so if we take and we say, okay, I'm going to assume that this operator is Hermitian, so it has some real eigenvalues. And these will be the eigenvalues or the eigenvectors of the Hamiltonian. So I can write down something like that. By substituting those back in, by applying the Hamiltonian, we see that this state has an eigenvalue. It's also an eigenvector rather for the Hamiltonian with the eigenvalue H bar omega times. Now, once I have that worked out, I can also look at the commutation relationship between the operator A dagger A and one of the other operators, say A, itself. So I can write down this, for example. And by using the product rule for commutators, I work out that this commutation relationship is just A. And so now if I look at, say, the something like the if I apply on both sides of this equation, the vector A itself, what I get is that this ought to equal A. And on the other hand, if I look at, well, what's the effect, what's just this part of this equation, because this is now the Hermitian conjugate of this vector here. Right? So if I can use this relationship and say, okay, well, what happens if I apply A dagger A to this vector? Right? I can use this commutation relation to work out that that is so what I've shown here, by doing this, by using this commutation relation, I show that the operator A probably should have chosen another letter for the eigenvalue. Now that I'm saying it aloud to everybody. Anyway, when I apply the operator A to this eigenvector of the number operator A dagger A, what I get is and also an eigenvector with the value lower by 1. That's why we use the nomenclature that A is a lowering operator. And so this takes one eigenvector of this number operator and lowers it by 1. We can figure out a similar relationship with the Hermitian conjugate V dagger, so that I get the following. And so the operator A dagger raises the eigenvalue by 1. And if we, lastly, to establish these relationships here, where I've the normalization, I just say, oh, well, if I look at this, if I look at the norm, that's just this, and so this is equal to A, which means that I have the following relationship. And lastly, I know that these have to be integers for the following reason. If I consider that this had a negative, let's say that this has a negative eigenvalue. If that has a negative eigenvalue, and I look at something like this, I'm going to just write it down with a negative sign explicitly. That would be a negative value, but this is the norm, right? I'm applying a vector to its Hermitian conjugate, to its dual, so that has to be a positive value. The norm of a vector has to be positive, so this is a contradiction. You can't have a negative eigenvalue. So that's how you know that these eigenstates are integral values, so that's why we can call this the number operator, and then that's why we get the nomenclature for raising and lowering operators that you do as well. So I know this is review, but I just figured when I was looking at it last night, I had kind of forgotten how to derive all that stuff, so I thought maybe it would be useful to go over it for everybody else. All right, so now because of these relationships, we can start with there is going to be some lowest eigenstate. And so that's usually we call that the ground state. And we can just apply the raising operator n successive times. And because of this recursion relation between the eigenvectors, to normalize it, we just divide by 1 over root n factorial. And that gives us the eigenstates of the number operator, A dagger A. Now, we can also write down an equation for eigenstates of the lowering operator itself, A. So now, it's a little confusing because you have a very similar notation. Usually if we use some kind of Greek letter here, that's indicating that we're talking about an eigenstate for the annihilation operator. And if we use an integer, or rather a Roman character, that's indicating that we're talking about an eigenstate of the number operator. Now, basically by direct substitution, we can verify that if I apply the annihilation operator to this state, what happens is everything lowers by 1. Well, if I apply A to this sum of alpha to the n over the square root of n factorial, what happens is I lower all these by 1 and I multiply by the square root of n, so I get something like this. And then if I re-index this sum, lastly, well, I'll have to put a -1 here to re-index that down. And that means that I have a constant factor alpha in the front. So after that, you see that that's just an eigenvector of the operator A. If we look at the statistics, if we look at now the probability of finding, if I were to make a measurement of the number, say if I were to apply the number operator to the state, and I were to look at the probability of finding a particular value, what you see is this exhibits Poissonian statistics, and the mean value is alpha squared. So this is Poissonian statistics with a mean of alpha squared. And if we look over here, if the number is large enough, if alpha squared is very large, this almost looks Gaussian, right? Poissonian statistics in large number limit become Gaussian statistics with variance of alpha. So the norm of alpha will be the variance if this is very large, so it approximates the distance. But for smaller values, Poissonian statistics are a bit misleading. Okay. Now, we're going to look at an application to a seemingly very different system, and that's the electric field inside a cavity. So if we have some nice boundary conditions here, the electric field will have to vanish at the edges. And so we have discrete modes. If we Fourier expand the electric field inside the cavity, we get discrete modes, and what we're going to do is focus on one particular component, one of these Fourier modes of the electric field. And so we can write down, and this normalization here doesn't quite make sense at first, but we can write down basically the electric field as sinusoidally varying along the z-axis. We're going to ignore the x and y dependence. And also we're going to pick a particular polarization. So when we talk about a single mode electric field, we're talking about one spatial dimension of variation, we're talking about one particular polarization already chosen, and we're talking about one particular frequency. Of course, in the real world, we have many modes, but oftentimes there's one mode that couples most strongly in the system, and so it's valid to just look at that. So using the boundary conditions, we can derive the electric field, and using Maxwell's equations, we can get the magnetic field from that. Now, we write down the energy density to get the Hamiltonian for the electric field. We first just write down the electromagnetic energy density, and then we integrate it over the entire volume. What you find out, if we made this kind of substitution up to some dimensional factors, basically what we get is something that looks like kind of a q squared, a position plus a momentum, a kind of a potential and kinetic term. And abstractly speaking, we've got these two, we've got the derivative here of some q, and that ends up becoming what we would call the momentum if we were talking about a traditional oscillator. So, we can quantize this using very similar quantization rules as before, where we've got, now instead of a 0-point position, we've got a 0-point electric field. So this is, in a sense, this is the kind of the electric field that adding a single photon to the system gives you an electric field of this magnitude. You see that basically this is proportional to the frequency and inversely proportional to the volume. So the smaller your cavity is, the larger the electric field you produce per excitation per photon. Basically, that's the notation. So here's the notation we're going to be using going forward. If we have a two-level system, that's going to be denoted with the subscript A for the frequency. The cavity frequency, this frequency of the electric field, is denoted by omega c. And then we're going to oftentimes externally pump the cavity, and so with a laser, and so we'll denote that frequency by omega alpha. Okay, so let's look at some of the interesting states of the electric field. Equivalently, these are the interesting states of the quantum harmonic oscillator, because now we've shown that they're basically equivalent. The Fock state is just the number eigenstate with a definite number of excitations, be they phonons or photons. Here's a small typo. Coherent state, this is the eigenvector for the annihilation operator A, and this should be a minus sign. This operator D is called the displacement operator, and it's unitary, so this needs to be a minus sign. But we'll show what this does in the next slide. Additionally, we can also write down what's called a squeeze coherent state by applying both a squeezing operator and a displacement operator. And the squeezing operator is quadratic in these creation and annihilation operators. And lastly, another interesting state is to just superimpose two, say, oppositely displaced coherent states, and that's a Schrödinger cat state. So these are some very basic, interesting states of either an oscillator or the electromagnetic field. Now we can also besides representing these as abstract vectors, we can look at a phase space representation by using something called the Wigner function. Now, this, at first glance, doesn't look, it looks a little bit threatening. You have this trace of the density matrix times this displacement operator, and then you're integrating it over the complex plane multiplied by the kind of a complex number here. But really, we can, for example, it's maybe not that enlightening, but if I integrate the Wigner function over the alpha plane, the complex plane, I get 1. So this is normalized to 1, for example. We can show that if I want to find the expectation value of an operator, remember the expectation is given by the trace of the density matrix times the operator. If I write down some function of A's and A daggers, there's a straightforward way to evaluate that by integrating over the Wigner function as long as you put the operators in normal order. Now, a picture's worth 1,000 equations, so let me take a look at some typical Wigner functions. Let's start with this one. The simplest state, the ground state, n equals 0, is just a Gaussian, a two-dimensional Gaussian. This is plotted in the complex plane here as a function of alpha real and alpha imaginary. So if I look now at a higher decided, yeah, go ahead.
Yes, is it the success time for the Wigner function? Since there is only 3 if.
Here?
Yeah.
Oh, I'll go through this graphically in just a second. Yeah. So, but that's a good question. This is the ground state. If I look at this, for example, if I plot now just the ordinary position wave function for the n equals 5 state, what that looks like is, and I'm going to exhibit why I'm a physicist and not an artist here. So if I look at the n equals 5 Fock states wave function, it looks like this. Okay, so it probably should be decaying a little bit more as I go out. But that's the gist, right? 5 nodes. Now if I plot psi of x squared, that's the probability density. And that looks like this. And if I were to, up to scaling, if I were to plot the position space representation of that wave function, it would have, just up to a scale, it would look the same. So if I look at this in a cross section, if I just take a cross section across one axis, I get that exact graph back. If I take a cross section along the other axis, I get the momentum space wave function. And so this is suggestive, this is not an exact analogy, but this is suggestive that what the Wigner function represents is a combination of both the position and the momentum representation. So because I can't specify position and momentum exactly at the same time, it doesn't make sense to look at a very tiny region, but if I kind of integrate over a large patch with area equal to several h bar of the Wigner function, what that roughly gives is the probability to find the system in that particular region of phase space. So the real axis is analogous to position, and the complex, the imaginary axis is analogous to the momentum. So that's kind of a very rough interpretation of the Wigner. It's called a quasi-probability distribution because it can. Okay. Now, if If I look at now, if I look at another simple example, if I just take the coherent state, the reason why we call this a displacement operator becomes a little more apparent when I look at the visual representation. The center of the wave function, the center of the graph, has just been displaced along in the complex plane. And so this displacement operator, basically the real part tells you, this displacement operator, the real part of this parameter alpha tells you how much I displace it along one axis, and the imaginary part tells you how much I displace it along the other axis. Similarly, the squeezing operator, the name for that becomes clear when I squeeze the state. What that does is it squeezes the graph. It changes the uncertainty. It changes kind of the spread. It decreases the spread in one direction, but increases the spread in the wave function in the other direction. If I were to look at the uncertainty relationships for this squeezed vacuum, if I were to look at the delta x, it would be greatly increased. If I were to look at the delta p, it would be greatly decreased, but the product would still be the minimum h bar over p. And lastly, the Schrodinger cat state, as we see, there's the two, what you expect kind of if you just added this to an oppositely displaced one. But you see there's some interference in the middle where those two intersect that you wouldn't have expected if you just looked at these two graphs. And I just thought, oh, there's going to just be two peaks. But in fact, there's some rather strong interference effects for these cat states. Now, as this amplitude, the amplitude of this parameter alpha increases, as you can see here, well, maybe you can't quite see it, but this is only -2, +2. If I increase that very large, those interference fringes kind of go away the farther I separate the cat states. So this kind of, these graphs I think help illustrate what the Wigner function looks like, and they give us some idea about what the kind of phase-space distribution of these quantum states. Now, let's move on to coupling two types of systems together using an electric dipole interaction. So the electric dipole is just Q times position, and then the potential that you get when you interact a dipole with an electric field is just basically the dipole moment dot. Yeah, that's the electric. That's just it. Now, if I basically the tricky thing in quantizing this is writing down the dipole operator, right? We already seen how to change the electric field to an operator, but to write down the electric dipole operator, it's basically an electric dipole moment, which could be complex, times the raising operator and the Hermitian conjugate, or rather the complex conjugate of that dipole moment times the lowering operator. So this is the electric dipole operator for a simple two-level system. Of course, if I have now a spin 1 or a spin 2 atom, it gets a little more tricky, but let's just keep it simple for now. Let's see. Now, the sign here, as you recall, the sign function, there's a spatial dependence to the electric field, right? It's sinusoidally oscillating. And so this coupling, this coupling strength between the atomic and the electrical system will have some spatial dependence. Now, sometimes we can ignore that, sometimes it's important. So as we go through, I think the first example, here's the full Hamiltonian, where we have the atomic Hamiltonian, we have the optical field Hamiltonian, and then here's this electric dipole interaction. So I'm going to show you one of the important tricks. The most important trick I found as a theorist, maybe, is the rotating wave approximation. And that lets us throw away things from our Hamiltonian, which is great. It makes it simple. So if I look at the Heisenberg picture, where I just look at the Heisenberg equation of motion for the operators, the Pauli operators and the raising and lowering operators based on these two terms, and ignore the interaction term for now, I can write down very simply the time evolution. The sigma plus operator will rotate, I think we should actually get a minus sign, but the sigma plus operator rotates one direction in the complex plane, the sigma minus rotates the other direction, and then the annihilation operator just gets this time-dependent phase. apply to it as well. Now, in the interaction, I have the product. I have 4 cross terms between these 2 operators. So let's just write out what they look like in the Heisenberg picture. And so 2 of the cross terms, it's kind of small, but 2 of the cross terms will have the difference between the cavity frequency and the atomic frequency. Right? When I write down the time dependence of these two cross terms, I get a difference between cavity and atomic frequency. On the other hand, 2 of the cross terms will have a plus sign between these 2 frequencies because these 2 are rotating in the same direction. Now, if the cavity frequency and the atomic frequency are close, this is nearly a resonant system. And so this will be a very small, slowly varying term. These 2 will be slowly varying because of this small detuning. And these will be very fast rotating terms because I have the sum of 2 large frequencies.
Yeah. Go ahead and go just the left.
Oh yeah, that's a good idea. The front one's on the left, actually. I think if you get that switch, it turns off those big white lights. No, sorry.
This one? Is it better?
Not everybody can have. All right. Yeah, that's much better. All right. The point is, if I look at what time evolution is given by the integral of the Hamiltonian, basically, right? I take the derivative of the wave function, for example, is I h bar, minus I h under h bar. And so, if I integrate the Hamiltonian, in a sense, if I have these fast varying terms, when I integrate this exponential, that gets divided. I divide these terms by a very large frequency. On the other hand, when I integrate these, if the detuning is small, I get a very small, I'm dividing them by a very small number. And so when I integrate the Hamiltonian, those terms become much smaller compared to these terms. And that kind of, in a very informal way, is how one justifies the rotating wave approximation. You can actually, this Hamiltonian is simple enough that you can go through and solve it with all the terms in place, but it turns out to be justified to throw away these fast rotating terms. That's a very common trick to use in atomic optics, is basically to look at products of operators and figure out which one's free evolution is going to cause them, these cross terms, to rotate quickly, and which one will be rotating slowly, and you can usually throw away the ones that rotate quickly. All right, so what we've got here now is a reduced interaction term, which only has 2 terms, and that is the Jaynes-Cummings Hamiltonian, which is the first big result of atomic optics, and that gives us a little rotating happy star because that derivation is done. All right, a few more slides from this first set of notes. Good. So we can kind of look at now. Let's say we have a really large electric field. I can kind of approximate the. Basically, I can approximate the electric field operator by its classical mean. So that's what I'm going to look at here. Is just take the operator. Basically, it amounts to taking the accretion and annihilation operators, replacing them by their mean, or equivalently looking at the just the classical electric field. And so in that case, what I pop out is the electric field at the dipole moment. Now if I look at, and so I get a Hamiltonian which only acts on the spin. Now that I'm ignoring the dynamics, now that I say light's classical, I'm kind of ignoring the dynamics of the electric field, and I'm focusing on the atomic reaction to this large classical electric field. Now, this is something that you'll see a lot in some of the optomechanics lectures in particular that are to follow, though it's pretty common. You have this bare coupling constant G that couples essentially a single photon to the atomic state. Now, if I replace this annihilation operator by its classical mean, which is large, I get effectively an enhancement of this coupling string. And so this is something that we'll come back to later. You can basically get an enhanced coupling strength by putting a lot of photons in your system. Anyway, replacing these by the classical values, you just get the essentially the dipole times the electric field. That's just the potential of the atom in this classical electric field divided by h bar, and that gives us a frequency, which is the Rabi frequency. All right. So what we're going to do is look at a kind of a vector model. So now I'm going to write down the three-component vector that has the real and imaginary parts of. Write down the density matrix. It's a 2 by 2 matrix that looks something like this. Right, and if I take the difference here, that's basically like sigma z, and then if I take the sum, the real part there, that's like sigma x, that's u, and if I multiply by I, that's kind of like sigma y. So that's suggestive that this is kind of related to the Pauli spin. Now, if I look at the first two here, they differ. They're time dependent and they differ in phase because I'm multiplying by I. They differ in phase by pi over 2 in the complex plane. And so the in-phase component will be responsible for dispersion, and then the out-of-phase component will be responsible for gain. So that's the component, the forcing which, like a harmonic oscillator, right, the forcing which follows in phase drives the system, and that which is out of phase is a damping effect. So we can now plug this back in and work out the dynamics from this interaction Hamiltonian. This is a bit of a cheat because what we've put here, this delta is just the detuning. And that we can derive from the Hamiltonian. This omega r is the Rabi frequency. We can also derive that from the Hamiltonian. And then we have, so this will just give us an oscillation, right? I have u dot equals delta v, e dot equals negative delta u. That's just oscillatory. Similarly, these derivatives are related to each other with the opposite sign. So that's also oscillatory. But what I've added by hand here are dissipation effects. A dissipation time where from either the excited or the ground state, the system can drop out to a third dark state, say, at different rates. So this is basically saying, okay, I've got this system which can be the ground state or excited state, or it can be completely in some third dark state here, and that's what this decay is happening. This decay channel is going to. On the other hand, if I look at a system where really this is the lowest level and there's only one excited level, this will have this is the inversion basically W. And if you look over here, it relates to how if the inversion is +1, all the atoms are in the excited state. If the inversion is -1, all the atoms are in the excited or in the ground state. So if you have just two levels with some driving, you don't want this to decay to 0. So there's going to be you have this +1 if there's no third channel for these states to decay to. And that will have, now you can solve these for their steady state values. Sorry, let's look at a pictorial representation of what this evolution entails. We're going to ignore these decay channels for now, right? And so if I throw away that term, without dissipation, what this Hamiltonian does is it just causes rotation on the Bloch sphere. And so if I'm completely on resonance, I get a rotation that goes all the way around the Bloch sphere in a great circle. If I'm a little bit off resonant with my driving, I traverse a smaller circle on the surface of the Bloch sphere. Because this type of, now if I put those terms back in, since this is a cross product, basically this is a rotation, right? But if I put this back in, what happens is I kind of gradually fall into the Bloch sphere because of dissipation. Okay, we're going to go back and we're going to throw in that spatial dependence, which we've been ignoring so far. We just looked at the spin, the interaction of the spin with the electric field at a single point. Now we're going to look at what happens when I throw in this motion of the atom. So the electric field has some spatial dependence. The phase can have spatial dependence, and the amplitude can have spatial dependence. If I plug that back into our Hamiltonian, what you get is something along these lines, where you have a spatially dependent Rabi frequency and then a phase. And then this is the, remember, the raising operator, sigma plus, just written out a little bit. Okay, so what about this momentum term? Even though the mass is large, the atom can still move around inside the electric field. So if we want, we can write down the force experience, which is just going to be the expectation value of, by using Heisenberg's equation of motion for the change in momentum, we can find the average force. And so this is a pretty complicated expression, so let's just break down what we're looking at here. There's basically two components to the force. There's a restoring force. This is basically the gradient in the Rabi frequency. Well, that's going to be the gradient in the electric field, right? If I plug in what the definition of the Rabi frequency is, that's a gradient in the electric field. Now, as you know, an electric dipole is pulled in the direction of the electric field gradient, right? And so that's what this component of the force is. It's kind of a force that pulls the dipole along the electric field gradient. On the other hand, this is due to changes in phase. So it's got an imaginary I here. So that's a dissipative force because it's out of phase with the restoring force. And you can see that breakdown more clearly here. And so if you plug in all the stuff we've done so far, you can actually work out what this dissipative component is and what this dipole force, this reactive force, the restoring force is. And if I look at, now if I say, okay, the mechanical dynamics of the system happens on a much slower time scale than the spin dynamics, I can look at the steady state values for the spin dynamics. And so I work those out. Basically, this S is kind of a fractional population. So basically, the important point is, by plugging this stuff in, you can figure out what the dissipative and the reactive forces may be. So let's see. So this gamma here is a new constant that we've introduced. This is basically the inverse of those times T1 and T2 for the system to radiate back to its ground state. So that's the inverse 1 over capital T that you saw. So that's that. Yes.
So what was happening on that and something else?
Oh, okay. So we're looking here at these kind of spin dynamics, right? And we weren't looking at all at the motion of the atom. And so now when we add this kinetic term, we're again looking at the motion of the atom. But the spin dynamics happen on a fast. The atom's got a large mass. It takes a while to move around. So the spin will equilibrate. It'll reach a steady state value, and that's what these equations are. So we're looking at the steady state value of the spin and how that drives the motion of the atom in the electric field. Now, this is just a bunch of complicated math, but let's look at the what's the effect? What effects does this have on the system? Now, one thing we get is Doppler cooling effect. So the phase, if we look in the frame of motion for the atom, the phase will depend on the velocity. The phase of the electric field is going to be dependent on the velocity. And so because of this, we look at our detuning isn't just what it was at rest, but rather it shifted, right? There's a Doppler shift to the detuning due to the motion of the atom. And so for small velocities, we can tailor expand this dissipative force about its equilibrium value, and what we get is a linear, a velocity-dependent dissipation. So we get just a nice linear dissipative effect. And this value alpha can be computed for two different scenarios. One where we have kind of a wave running through and the atom's going in the opposite direction. Again, this particular form isn't all that important. And we can also see what's the effect if now I have an atom sitting in a cavity with a standing wave and the atom is moving along in that standing wave field. And so these are just kind of the dissipative coefficients that you get in those two different scenarios. Now, next is again, we're going to take a look at a picture. This gives you an idea, basically, heuristically, of how this Doppler works. If the atom is moving, if you have two beams of equal intensity shining on your atom at the same frequency, if the atom moves towards one, that gets blue shifted. So the atom's being hit by photons with greater, in its frame of reference anyway, it's getting hit by photons with more momentum going one direction than the other direction. And so that's going to stop it from moving in that direction. There'll be a net force going the other way. On the other hand, if I have the atom moving in the other direction, now the light coming from the other direction is blue shifted to the atom. And so it experiences a greater force going back that way. And so what we get is a nice linear dissipation on the atom's velocity. So this is called Doppler cooling. This allows us to trap atoms. And we can do this same thing in 3 dimensions, where as the atom is kicked in whatever direction, the radiation pressure basically pushes it back to its equilibrium position. Okay, now we're going to switch gears back to the Jaynes-Cummings Hamiltonian again, and look at basically what are the solutions to this Jaynes-Cummings Hamiltonian. So if you look carefully at this system, the sigma z will preserve whether the system's in the excited or the ground state. The number operator A dagger A will preserve the number, and the only thing that can change either of those is these two products, this cross product term here. Now, if I can't read that, that's a sigma plus, and that one's a sigma minus. The first one's a sigma plus. That's coupled with the annihilation operator. So if I annihilate a photon, I excite the atom, and then the other operator says, well, if I have an excited atom and n photons, I add 1, but I knock the atom back to the ground state. So that manifold here, this two combined state, this is a combined state of the atomic and the optical field. This is invariant under the Hamiltonian. Yeah?
What's a manifold?
Oh, sorry. It's like a vector subspace. So like I have these two quantum states, and they determine a subspace of the whole Hilbert space. So that's a manifold, basically. Actually, a mathematician would, be mad at me because that's not. A manifold is some other thing. This is a subspace of the Hilbert space. It's a subspace which is invariant under the action of the Hamiltonian. Okay, because the full state, I go from 0 to infinity photons, and I have for each of those, I can have the atom and the excited or the ground state. So that's 2 infinities of basis vectors, but the Hamiltonian, I can look at it acting only on those two, and it won't ever leave those two. It starts there. So the solutions, now if I can actually just directly evaluate, well, what's the solution? What are the eigenstates of this Hamiltonian? And they're going to be linear superpositions. They're going to be admixtures of these two states. And there's two limiting cases. So we can, again, it's a straightforward exercise to work this out. But we can interpret this now if basically if G times N is small, right? That's going to be a weak coupling limit. So that's the weak coupling case where I have few photons and therefore they're coupled weakly to the atom. Right? And what I get is then that this angle, if I take this to be 0, this angle is essentially just 0. Okay? And if I plug in theta to 0, what I get is the first state is just the ground state of the atom with an extra photon. And then the second state is the excited state with one less photon. And so that's just kind of that's the absence of an interaction. You just have these two separate states. But this will eventually, for large enough photon numbers, become much bigger than the detuning delta. If I look at very high photon numbers, this eventually becomes very large. And so that causes this angle to approach, or this cosine rather, approaches 0. That means the angle theta is pi over 4. It's 45 degrees. And then in that case, if I plug that back in with very large n, I get just equal admixtures with opposite sign. So again, as n goes to infinity, this angle, or rather twice the angle, goes to pi over 2. And so this angle here becomes pi over 4. So I get equal admixtures of excited and ground state for the atom with just opposite sign. And so we can see that for basically for different detunings, or rather for different light detunings. You basically see that you go from non-interacting states to maximally coupled states. Now, we can do the Schrodinger evolution for the whole system in the very simple case where we just have initially an excited atom and no photons and the detuning is 0. If we look in that case, what we have is just a sinusoidal oscillation. Yeah. With 0 photons, we have no electric field, but we still get these, these should be proportional here. Anyway. With no photons, we still get these oscillations. The atom still oscillates between its excited and ground states, even though there's no electric field driving it. There's no photons. And if I look at the Hamiltonian, there's no photons in the system, right? This, I would expect there's no interaction. And so this operator sigma z ought to leave the excited state excited and the ground state in the ground. Right? Without this interaction term coupling the excited state and the ground state, they just sit there and there's just a phase as they rotate in opposite directions, but the population doesn't change for the excited and ground state. So this is a kind of an interesting scenario where basically I have the atom, it goes to the ground state and emits a photon into the cavity, but then that goes back, apparently gets reabsorbed. This can be a bit puzzling because you'd expect, in the absence of photons, there not to be an interaction. But the reason is that the atom is interacting with the electric field modes, even in the absence, even in vacuum. There's still, the electric field modes are still possible, and the atom can still decay into those channels. So I can take the free space case where now there's a bunch of modes, and they'll all have very similar kind of interaction Hamiltonians, where again I annihilate one photon in one particular mode, and I excite the atom, and then the Hermitian conjugate is the reciprocal relationship. And also note that the coupling strength for this interaction will be frequency dependent. That's why there's the G sub S. This S is the different optical modes. They have different frequencies, and they'll couple differently with different strengths of the atom. Now, I can just use the same. I can derive the same Jaynes-Cummings Hamiltonian, and I can do the Schrödinger evolution of the system. And I can get it all analytically after I do the rotating wave approximation. Now, the tricky part is I can now formally integrate the Schrödinger equation. And I'm going to do some mathematical tricks here. Basically what I do is I say, okay, this integral, this basically is approximately the sum over modes goes to a continuum integral. This integral over frequency, this will be basically integral over frequency. When I integrate over frequency, this becomes a delta function, right? Integral of e to the I omega minus omega prime integrated over all frequencies gives me essentially a delta function for whatever else is in the up to factors of 2 pi and such, for whatever else is in the exponential. So that gives me a delta of t minus t prime, and then when I do this time integral, after turning this sum into a frequency integral, that delta function picks out the original time, and so this gives me a decay of the population due to this spontaneous emission. Now, when we talk about open systems, we'll come back to this idea that the system can decay over time. Now, if I plug in all the things carefully with the density of states and the coupling, the atomic coupling and the detuning plugged in very carefully and do this integral and get all the numerical factors correct, this is what I get for the spontaneous emission rate in free space. It's dependent on the atomic frequency and its dipole moment, basically. That's it. Now, this isn't fundamental quantity. If I put it in a cavity, I can change the density of modes. And changing the density of modes changes numerical factors in the sum. And so I can give enhanced spontaneous emission. I can inhibit the spontaneous emission. I can even make it reversible. If my cavity, if I put this atom in the cavity, the photons can bounce around and be reabsorbed and excite the atom back. And so this leads to the many exciting problems in cavity QED and circuit QED. And I think this notice is to remind you that Steve Gervin is going to be, right here, Steve Gervin is going to be talking about this in his talks a little later in the week, about basically manipulating the geometry, manipulating this coupling to change and even reverse the sign and such of this spontaneous emission. All right, so very briefly, we work out what the evolution of the Jaynes-Cummings model is of this system combined with the atom, the electric field. So let's say we pump it within a coherent initial electromagnetic field comes in. I can work out the time evolutions. It's straightforward, and I get this kind of population. And you see that this is rather the total probability for the system for the atom to be in an excited state based on its interaction now with all the photons. So instead of limiting myself to this particular two-state submanifold of the Hilbert space, I'm saying, okay, I'm applying it a coherent state. As you recall, coherent state has probability for finding anywhere from 0 to an infinite number of photons. So I have to consider all those. And then I'm basically adding basically adding now all the probabilities, all those coefficients for finding the atom in its excited state. So these all oscillate sinusoidally for each ground state, comma, n+1, and excited state, comma, n photons. Those two probabilities oscillate back and forth sinusoidally, but each of the frequencies, they're not commensurate because of this square root here, right? So the frequencies, this is, even though each of these terms is a periodic function that I'm adding together, what I get, the sum isn't periodic because these aren't rationally commensurate periods, the oscillations, these different terms. And so the probability for the system to be in excited state, it decays to a half. In other words, it's just 50-50 admixture, but if I keep going, if I keep looking at the system, and there's no loss of this coherent field, the coherent field in the cavity can now cause the system to get re-excited. These oscillations will come back, but not in a straightforward periodic way, again, because of this square root here, the frequencies aren't commensurate. So I get this collapse and revival of the wave function. And in a high-quality cavity, we can actually see this experimentally. All right, that does it for lecture 1. I think we need a break. So please, any questions about anything? I went kind of fast. So. No? Okay. Well, we'll see you guys again in 10 minutes.
And Steve will be here all the time, so you can ask him anytime you want. And he goes to bed late, so you can.
Yeah, I know. Thanks, and I get to do the 9 a.m. lecture. All right. Well, we'll see you guys in a few minutes.